Hi, I wanted to do a quick derivation of the Lorentz transformations that we've been talking about with relativity. And as just a reminder, this is a set of transformations from one frame that I'll call the S frame to another frame that I'll call the S prime frame. And in the S frame, we have coordinates x, y, z, t, describing any position and time. And in the S prime frame, we have the same things, but primed, x prime, y prime, z prime, t prime. And these are going to be a set of transformations that allow us to move between these different frames. And of course, this S frame moves with a relative velocity v with respect to the S frame. We're going to lay out a couple ground rules for what we want these transformations to be. We want to make sure that no frame is special, one of the core tenets of relativity. So any transformation from S to S prime should look very similar to a transformation from S prime to S. The only thing that should really change would be maybe the sign of this velocity term in those equations and just exchanging the primes and the unprimed coordinates. Everything else should look the same. And again, this comes from the fact that we don't want a special frame, so if there was a frame in which the transformations looked different than any other frame, then that would imply that something was special about that frame. So we don't want that to be true. We also want there to be a one-to-one relationship. So if I have some coordinate x prime in the primed frame, I want that to correspond directly in a one-to-one fashion to some coordinate in the x frame. And what I mean by that is, as an example, and I'll use this example for my third point as well, let's say I have x prime equals x squared is a hypothetical transformation, and t prime equals t in this very simple example. So this is a case where we would have a kind of a quadratic relationship of some sort. And then I have the coordinate x prime equals 4. Well, obviously that corresponds to two possibilities for x, plus or minus 2. And so this is not a one-to-one relationship. We don't want that. We want, if I tell you what the x prime coordinate is, I want you to be able to calculate exactly what the x coordinate is. So anything where this is not going to be true, we don't want. And then the third thing that we want to be sure of is we want to be able to agree on forces. This is going back to one of the core tenets of relativity again, that say you were floating out in space somewhere very far away from any other object, and you were performing a set of experiments, and then then someone else is performing the same set of experiments, but in a frame moving at constant velocity relative to you. So you're both in what we would call inertial frames. You should agree that the acceleration you experience would agree with this other person moving relative to you. Will also experience those same accelerations so that we have the same forces. So if we use again this example, we can see that in this case, if I wanted to, say, calculate a derivative of these things, so I'll say u prime, the derivative dx prime dt prime, would be equal to, in this case, 2x dx dt. And so we've already got some extra stuff going on here. I'm going to call this 2xu. And if I take a second derivative of this, then I'd say du prime dt prime is a prime. That's the acceleration in the primed frame. That is going to be now 2 and I'll have to do a a product rule here. We will say this one here becomes another dx dt term, so that's actually a u squared from that first piece of the product rule, and then we would get just a 2xa, where this a is the derivative of u with respect to t. So now we can see that we have this extra piece here, and then all this stuff going on that says a prime is not in general equal to a. And so we don't want that to be happening in our transformations. So one type of functional form that would work is a linear form. And in this case, I'll say that my linear form, I'm going to just do as general as possible. Some ax plus bt, where this a and this b are just some sort of constant. So I don't mean acceleration for this a. I'm saying this is just some constant a. And we can then say, well, what can we say? We can say, let's look at an event that happens at the origin of the S prime coordinate system. And if it's moving, if it's at rest in this system, so we would say then that its x prime coordinate is 0, its x coordinate must be changing. And since S prime is moving away from the S frame in the positive x direction with a constant relative velocity of v, that means its x coordinate will be exactly changing like this. It will be increasing with time, and it will be moving at speed v. Okay, so now we can just plug these things in. We say the x prime is 0, and then we'd say times a times x. We know x is vt, and then that's plus bt. So then we can just solve for, say, we can cancel our t's and say that b is just equal to minus a v. And so this b is just related to this a by this constant v that we've already talked about being the relative velocity of our coordinate system. So I can rewrite this linear relationship in just in terms of one unknown constant a, rather than have both a and b. So I'll say a, and then we've got x, and then we have here, for b, I'm going to put minus a v times t. Or rather, I'm going to factor out that a, so x minus vt, like that. Now notice here that this looks very similar to, say, our Galilean transformations that we talked about. And in the Galilean transformations, a would be 0. A equals, or sorry, nope, not 0. A equals 1, is what I mean, for Galileo, I'll say. But we'll try to do this a little bit more carefully now using Einstein's second postulate, that c is constant in all frames. All observers see light move at a constant rate. And I'm actually going to write out, so here I've got x prime equals a x minus v t as one equation. I can actually write the inverse transform, say x related to the primed coordinates. All I have to do is swap the sign of v, like I said before, because now we're talking about from x's perspective, how does x prime move, and how does x prime, from x prime's perspective, how does x move? They're just oppositely directed motion. And I'm still going to have this constant a, but I can just swap the primes and swap the sign of the velocity term. to swap between these two coordinates. So I've got now the transform and the inverse transform. And I'm going to use this second postulate and say, what if at some time t equals 0, so this is in the unprimed coordinate system, the primed coordinate system is exactly overlapping. So here s equals s prime at exactly, or sorry, I should say overlaps, not exactly equal, but x prime equals x at t equals 0, and that would also imply t prime equals 0, because if we compare our clocks right at that same time, they will overlap, assuming they're cospatial. So then frames overlap, and at that instant in time, a light bulb at the origin is going to flash and send out a spherical wave pulse at the speed of light. So a single pulse of light goes out. And because we know that c is constant, both observers will see the position of this spherical wavefront moving outward as propagating at speed c. So the coordinate of where that spherical wave pulse is at any given instant in time will be in the s frame, x equals ct, and in the s prime frame, x prime equals ct prime. So we're going to use this and our two relationships here to derive the relationship between these coordinate systems and the transformation. So let me use both of these things. And first, let me say x equals ct equals here a x prime, which I'm going to write out as ct prime. And then I would say plus v t prime, like that. And I want to then just solve this. So here I'm going to say ct equals a c plus v t prime, just factoring out a t prime. I'm going to solve this for the ratio of t to t prime. So t divided by t prime. That's just dividing both sides by c and dividing both sides by t prime. So I get a c plus v over c. Okay, I'm going to set this aside for just a moment, and I'm going to do the exact same thing, but now in the primed coordinate system, where I know x prime equals ct as well. Sorry, ct prime, I should say. And then I know x prime from our relationship here is also a x minus vt, and I'll again replace this x with, I know it to be ct, because in the x coordinate frame, that's the location of that pulse in the unprimed coordinates. And I'm going to do the same thing and factor out a t here. So I've got a c minus v times t. And I want to solve for this for the exact same thing again, t over t prime. T over t prime now with these will be, let's see here, make sure I've got this all right. We're going to divide by t prime and divide by this whole a times c minus v. So we're going to get c over a c minus v, like that. And now we've got two expressions, both equal to t over t prime. I'm going to set those equal to each other. Over here, we're going to have a times c plus v over c, and then we're going to set that equal to c over a c minus v. And I want to solve for a, because a is that unknown constant that we don't know what to do with. And if I multiply both sides here, so I get a squared on this side, I'm going to multiply this c over here, c squared, and then I'll divide c plus v to get c plus v times c minus v, which you might remember from some algebra classes that if you have c plus v times c minus v, you're going to get c squared minus v squared. Okay, not bad. We're pretty close. We just need to take a square root. But I'm actually going to do one other thing, and I'm going to actually divide both sides by, or top and bottom by c squared. So then that we get a squared is equal to 1 over 1 minus v over c quantity squared. And you might now kind of see why we were doing that, because this is starting to look a little familiar. That means a is equal to 1 over the square root of 1 minus v over c quantity squared, and that is our Lorentz factor gamma. So that looks pretty nice. And now all we have to do is just put that back in here. I'm going to flip my page though, so if you need to pause to look at anything, but I'm going to flip. So our transformations now look like x equals gamma x prime plus vt, and x prime equals gamma x minus vt, like that. And we know that there's a little bit more to these transformations because we need to find a relationship between, say, t and t prime, and we're actually going to use these relationships to do it. So, to do that, let me take this first one, x equals gamma x prime plus vt. I'm actually going to write in all of this for that x prime. So I'm going to write in gamma x, and I'll just factor this gamma through. So gamma x minus gamma vt. Oh, sorry, don't want to close that parenthesis quite yet, because that is just my x prime, and then I have a plus vt there. Wait, sorry, this is primed, that's primed. Yes. Make sure to get your primes and your not primes correct. So this one's primed. And so now we're going to do a little bit more here. I want to first, I've got gammas here and here. I'm going to factor out a gamma there from everything. So we get gamma squared. This will be x minus vt, and then plus vt prime over gamma, because there wasn't a gamma on this term and I took a gamma out of it. Okay, so now I'm going to divide this gamma squared to the other side. So we got x over gamma squared is equal to x minus vt plus vt prime over gamma. And remember what gamma is. We know gamma, if I say gamma squared, that's just going to be 1 over 1 minus v over v squared over c squared. So if I say x divided by gamma squared, that's just x times 1 minus v squared over c squared, like that. And if I expand that, that's x minus x v squared over c squared. And all of that is equal to this, which has just an x. So I'm just going to actually cancel the x on both sides of that equation. And then what remains, everything has at least a factor of v. So I'm also going to divide one factor of v from everything. So here, I did a lot of canceling there. So I'm just going to rewrite this so we are all on the same page. So this is now minus xv over c squared is equal to minus t plus t prime over gamma. And I want to solve, say, for t prime in terms of the other things. So I'm going to put the t to the other side. So t prime over gamma equals t minus x v over c squared. And finally, multiply everything by gamma again to just get t prime equals gamma t minus x v over c squared. Well, there we go. That actually is one of our transforms. It now has how to solve for t prime in terms of all of the unprimed coordinates. And finally, to find the other of these, finding t from the t primed coordinates, we just need to swap all the primes and swap the sign on v. So then t is gamma times t prime plus x prime v over c squared. And there we go. Now we've derived fully all of our Lorentz transformations. So again, just to round this out, let's write this one last time. This is like this, and make sure I'm getting all of these signs correct and primed coordinates. There we go. And of course, we know that motion in the transverse direction is not affected, so we have just y prime equals y, and z prime equals z, and so on. Okay, hopefully that was helpful.